Well, hello everyone. This is going to be the second part of the lectures having to do with closed abundance estimation, following from the part A, which I posted a couple of days ago. And just to sort of refresh where we are and where we're going to go, the basic objective here with closed populations is to estimate abundance. With a closed populations where there is no entries and there's no exits rather, then n is a constant. And when n is a constant, then you can handle all sorts of challenges, or at least you can make an attempt to handle all sorts of challenges with respect to the estimation of abundance. And the single most pernicious challenge, which has been around pretty well since the outset, is this problem of heterogeneity in detection. So the usual models for abundance estimation, like everything else, make the assumption that everybody's flipping the same coin. And under that assumption that everybody's flipping the same coin and that each coin flip is independent of everybody else's coin flip, then there are lots of things that we can do that are generally pretty robust and lead to estimates which are both precise and unbiased. But it based on the assumption that everybody's flipping the same coin. So what if they don't? And so the idea of heterogeneity is this idea that the coins that the animals are flipping differ. And we might expect them to differ under normal circumstances, but what we often need to do then is explore the degree to which those differences are going to influence the estimates that we get, either in terms of precision or bias or both. And occasionally heterogeneity will have no impact whatsoever, and occasionally, as we'll see with the abundance estimation problem, it can have a fairly significant implication on precision and bias that we need to account for. So let's talk about heterogeneity detection and how it influences abundance estimation. So the notion of heterogeneity is defined sort of formally as the quality or state of being heterogeneous. It's composition from dissimilar parts, disparateness, differences. All right. So we imagine the population consists of different animals with different kinds of coins that they're flipping, and that heterogeneity is something that we might need to account for in our estimation. All right. So here's a cheap visual to show you sort of the extreme of the heterogeneity. The assumption, of course, is that they're all the same, but if you have some that are different, what happens? Okay, so let's look at this sort of conceptually first. And it turns out that the main problem with respect to heterogeneity and how it influences abundance estimation can be traced back to something which has been around for a long, long time called Simpson's paradox. It has nothing to do with Homer and family or Springfield. It's simply called Simpson after the statistician who first sort of described this. So Simpson's paradox, what is it and why is it important? Well, suppose that you have a population which consists of two types or two different subpopulations. Now, you don't know that there are subpopulations, but let's just pretend for the moment that we do, and we're going to call them A and B. And so the overall population that we have consists of certain proportions of A and B. So we'll imagine to begin with that 95% of the population consists of type A individuals, and 5% of the population consists of type B individuals. Okay, so mostly type A with a small percentage of type B. Well, what's different between these two types? Well, for type A individuals, they have a survival rate of 40% and a recruitment probability of 1.2. Well, what that means, what recruitment means, is that for every one individual at the start, how many individuals come out at the other end? So most of you have seen things related to recruitment before, but that's how we're going to define it here. So for type A individuals, each individual that survives will produce 1.2 offspring. So that's the recruitment. So survival probability and then the recruitment. Type B, on the other hand, there's only 5% of them, but they have a much higher survival rate and a much greater recruitment. So type A, most of the individuals are type A, low survival, low recruitment. Proportion are type B, high survival and high recruitment. Now, if you simply average these values, and these averages that we see here are weighted averages. So if you calculated the survival probability for 100 individuals, 95 of them would have a survival rate of 40%, 5 of them would have a survival rate for 80%, and so the weighted average over the entire population, so pooling over the subpopulations, would be 42. For recruitment, much the same kind of story. We have 95% of the population make 1.2 babies per capita, 5% of the population makes 4 babies per capita, so the weighted average recruitment is 1.34. Okay, so why is that a problem? Well, that's a problem when you're actually trying to figure out what the population is going to do, because when you sample a population, you don't actually know that there are subpopulations, and you can't look at an individual and say, oh, you're a type A individual or a type B individual, and that's going to have a pretty profound impact on the estimates that you make. So here's a demonstration of that. Suppose that at the start in our population, we have 950 individuals that are type A and 50 individuals that are type B. They just happen to follow the 95% and 50% composition model from above. So 1,000 total individuals, of which 950 and 50 would be type A and B respectively. Given the survival probability for type A individuals, from those 950, we would expect to see 380 at the end of the experiment. Of those 380, because a type A individual makes 1.2 babies, 380 times 1.2 is 456 individuals. Okay, so 380, the number that survived, plus the number that they make, the number of babies that they make, 380 plus 456 is 836 total individuals that are type A at the end of one time interval. What about the type B individuals? Well, we start with 50. Type B individuals have a survival probability of 80%. And so of the 100, we would expect, or excuse me, of the 1,000, we would expect to see what? Well, in fact, of the 50 that we have that are type B, I already got ahead of myself there, we expect to see 40 at the end. And of those 40, remember, the type B individual makes 4 babies per capita, so 40 individuals would yield 160 recruitments, so we would expect to see 200. Okay, so what is 836 plus 200? 1,036 individuals. All right, so that's how many we would actually expect to see. But if we start with 1,000 individuals and we use the weighted survival probability of 42 or 0.42, we would expect to see 420. The weighted recruitment is 1.34, 563. So 420 plus 563 is 983. Well, why is that important? It's important because if we looked at the average population aggregating over A and B, the population would appear to be declining when in fact it should be growing. And it would be growing if the heterogeneity had been detected. So this is the problem. What the average represents aggregated over the different types of individuals and what the population is really going to do are often quite different. And that's the problem. So what if animals really do have different coins? So I'm going to look at this sort of algebraically for a couple of slides here, just to get your brain wrapped around a few key ideas. So we'll start by assuming individuals have different values of the encounter probability P. The sample, if you think about it, is going to tend to catch individuals that have a higher latent value of P. So a latent value of a parameter is the parameter that's sort of unique to that individual. So imagine somewhere on the individual's DNA is some coin, and some of the individuals are going to have a DNA that when they flip that coin that says, I'm easier to catch than some other individuals. Okay, so if you have some individuals that are easy to catch and some individuals that are harder to catch, then any random sample of the population that you make will tend to catch individuals that have a higher latent value of P. And that's going to bias the overall estimate of P high. And if you think about it, it should make sense. You're mostly sampling the individuals that have a high level of P, and you're missing the individuals, because you're not sampling them, that have a latent probability of a low P. Now, why is that a problem for abundance estimation? It's a problem because we need to remember that the canonical estimator for N is C, the count, divided by our estimate of P. So if P is biased high, then the estimates of N will be biased low. So if something happens, and this something in this case is heterogeneity, that makes the p-value that you estimate too high, then because the count will stay essentially the same, then the estimate will be biased low, since a constant divided by a bigger number leads to a smaller fraction, so n is going to be estimated too low. Now, let's look at this by means of a simple numerical demonstration. If we assume that true n is 100, so that the P is this, and we'll assume that the P is the same for all the individuals, which is the underlying assumption, no heterogeneity, same coin, then what? Well, recall, and this is going to become important as we progress through here, that P star is 1 minus P to the K. So 1 minus P is the probability of missing the animal. 1 minus P to the K is the probability of missing it each occasion, each of K occasions, and then 1 minus that is the probability of being detected at least once. So this was discussed at some length in part A of this lecture. Okay, so that's P star. And remember, the estimate of abundance is the count divided by P star. So if P is 0.3 and K was 5 occasions, then P star is 0.83193, meaning the probability of being encountered at least once, given that there are 5 sampling occasions, is about 83%. So we would expect to encounter 83.193 individuals out of 100 at least once. Right? So that's our expected count, and our P star is 0.83. So if we took the expected count and divided it by P star, we get 100, which is exactly what it should be. Okay, so this is the situation where all individuals have the same coin, no heterogeneity, same p-value. What if we have the situation, though, where instead of everybody flipping the same coin, now we've got heterogeneity? We'll pretend that we have 2 types or classes of individuals, those with a high encounter probability of 0.4 and those with the low encounter probability of 0.2. Now, I picked those values because if you look at it, 0.4 and 0.2, the mean of those 2 values is 0.3. So in the preceding slide, when P was 0.3, if everybody was flipping the same coin, then we would expect to encounter 83, and then we would get an estimate of 100. So we get an estimate that's unbiased. But now we're assuming that instead of everybody having 0.3, some of the individuals have 0.4, some of the individuals have 0.2, the mean is 0.3, but now we have heterogeneity. Okay, so let's assume to begin with that our population consists of 50 high probability individuals and 50 low probability individuals. So our sample size is 100. The true population size is 100. All right, so what would P star for the high individuals be? So we simply take 0.4 and put it into our equation for P star. So put 0.4 in there, K is still 5 occasions. If we do that, P star for the high individuals is 0.92224, meaning for those individuals with a high latent probability of encounter, there's a 92% chance that you'll be detected at least once. Conversely, for the low and latent probability of encounter individuals, then the probability of being encountered at least once, P star, is 0.67. So big difference. 92% chance for these guys, 67% chance for these guys. Okay, so for the high encounter probability individuals, we would then expect 46.112 of those individuals to be encountered at least once. For the low probability of encounter individuals, we would expect 33.616 of the 50 individuals to be encountered. So 46.112 plus 33.616 is 79.728. So if we go out there and we look at this population, we would expect 79.728 total unique individuals. In other words, M at T plus 1, which was introduced in the last lecture, would be 79.728. That's our expected value. Oops. So what? All right, well, the mean encounter probability for the sample would be what? It's going to be a weighted average of the 2 types of individuals. We expect to see 33.616 for the low P individuals, 46.112 rather of the high individuals. The total number of individuals that we would expect to see based on the preceding slide, 79.728, that's this value here in the denominator. Okay, so the weighted average, what we would actually expect to see for our encounter probability would be 0.31567. All right, so the sample P star then would be 1 minus 0.31567 raised to the 5th power, and then 1 minus that is 0.8499. Now let's look at that value, 0.8499, and go back here and compare it to what we would have gotten if we had assumed everybody's flipping the same coin. If everybody flips the same coin and the latent probability is 0.3, then P star should be 0.83193. Here, we're assuming there's heterogeneity. They're not all flipping the same coin. And so the P star we would expect to see is 0.849. It's a little bit bigger, or 8.5, I guess. What does that do? Well, the denominator is a little bit bigger, and so that creates a negative bias in the estimate of n. Instead of 100, we get an estimate that's 93.806. So it's biased, albeit only by 7 or so, or 6 or 7 or so, but it's still negatively biased. All right, so what's another factor that we have to keep into account? Well, let's run through the exact same exercise, but now we're going to make P for the high individuals 0.5 and for the low individuals 0.1. The mean is still 0.3, but the variance now is much, much bigger, okay? So we'll assume the same starting number of 50 high individuals and 50 low individuals. We have a P star for the high of 0.968. For the P star for the low is 0.4095. That's the expected number of the 50 high P individuals we expect to see. There's the expected number of the low individuals that we expect to see. And the total of those two values combined or summed together is 68.913. We repeat the same exercise to calculate a weighted average of the sample. So it'll be 0.38. P star is 0.9092. 0.9092 is even lower. So our estimate of n is even smaller than it was, even bigger negative bias. Instead of 100, or even instead of 93 or 94, it's all the way down to 75.8, which is a very, very strong negative bias. So this is the problem. This is the general problem. And what you actually see here in this graph is just how big a deal this could be. So on the vertical axis, we have the expected abundance n, and on the horizontal axis, we have the variance in the detection probability. Right? So here we're assuming the same mean, but we're looking at different variances. So what you'll see are two things being represented here. Clearly, as the variance increases, the bias goes up. Okay? And the magnitude of the bias is worst when you're dealing with a situation where the expected detection probability is low. Right? So the higher the detection probability, the less of a problem that high variance in detection or high degrees of heterogeneity is. So the worst possible scenario that you could have would be lots of heterogeneity and a very low encounter probability. Where would you most likely run into this problem? Well, you're most likely going to run into the problem for small threatened populations where the detection probability tends to be pretty low. And because you don't have very many individuals, the impact of heterogeneity is going to be much bigger. So this is a huge problem. And so for a lot of reasons, we would like to see if we can solve for this problem in some fashion. In theory, then, the way that you have to handle that is you need to have some more flexibility in your model. And in principle, that's straightforward. So here is the canonical estimator for abundance based upon what we've talked about before. We have the count divided by essentially our estimated P star. Now, again, this is fine if everybody's flipping the same coin. If they're not, then you need to modify this to allow for heterogeneity. In the extreme, what you might imagine is that every single individual has their own latent probability of encounter. So if that's true, then in theory, you might imagine that you would have the count for that individual divided by its latent detection probability plus the count for the second individual and so on. And so you'd end up with an estimate of abundance that would be essentially each individual count divided by each individual's detection probability. Now, in the worst case, where every individual has its own detection probability, this creates an insurmountable problem. It's insurmountable because that would mean that each one of the terms in this equation would be one individual. And you can't estimate a parameter from a sample size of 1 because you have 0 degrees of freedom. There's no way you can do that. So this model up here is the one that says everybody is flipping the same coin. This is the model that you might imagine building where every single individual has their own detection probability. And the reality is the former is naive, the latter is not possible, so we need to sit somewhere in the middle. And for those folks who took 4100, we saw a similar sort of thing. We could go back to 3100 models and just do dNdt and pretend everybody was the same. Or we could imagine a completely individually based model, but then we have the same problem that's being described here. How do we estimate the parameters? Or we go somewhere in the middle. For the 4100 models, we ended up using matrix models as essentially something that's in the middle. It aggregates individuals in certain ways. It's not completely individual, but it does account for some of the heterogeneity. So in fact, a matrix model is a model that explicitly handles heterogeneity by assuming that a 2-year-old and a 3-year-old might make different babies or have different survival probabilities. We need to do the same sort of thing here for abundance estimation. How do you do that? Well, obviously, part of what you're going to do, maybe it's not obvious, but I'll say it, it is obvious when you really start to work on it, that one of the things you should do is standardize your sampling such that you're likely to catch everyone with the same probability. You do whatever you can to reduce the chances that some individuals are going to be more easily caught than other individuals. All right. And that's fine, except it's hard to do, and it's generally going to be difficult to imagine what the sources of variance are so that you can design your sampling appropriately. So beyond that, there are really two classes of approaches, and the vast majority of the literature splits between one or the other of these. There may be observable sources of heterogeneity that you can account for by means of an individual covariate in a Huggins model. So remember the Huggins model, because it conditions abundance or F0 out of the likelihood, you can actually use individual covariates, and that's one of the singular advantages of the Huggins model. So if you can observe a covariate, and by observable we simply mean something that you could see, and if you can see it, therefore you can measure it. If you have an observable covariate that you believe influences the probability of detection, then you could include those covariates in your design matrix and account for the heterogeneity directly. It's just simply part of the linear model. So a classic example would be if the body size of an animal determines to some degree its probability of being encountered, then if you had body size measurements for your individuals as an individual covariate, you could use those as covariates to account for some of the heterogeneity. There's all sorts of different ways that this could be done. If you have a trapping grid, for example, you might use the distances of the traps from the edges of the grid or from the edges of home ranges. There's all sorts of things that potentially you might measure if you believe that those covariates can actually influence the probability of detection. In principle, that's straightforward, but it's not always going to be obvious what the covariates are that are going to influence detection probabilities. Okay, so the other approach is just to say, well, forget it. We're going to treat all sources of variation as unobservable. We can't identify it, we can't control for it by sampling, and we can't measure it. And so what we're going to do is instead we're going to pretend that the individuals are being sampled from some underlying probability distribution, and then we're going to use that probability distribution to deal with the heterogeneity. So this is what a lot of people would call model-based inference. You're making inference based upon a model where you pretend that the animals are coming from some sort of distribution. So designed versus model-based solutions. So observable sources of variability. Let's start with that one. So what are the things that we can do? Well, time. We might imagine there's temporal covariates, like it's rainy, or it's dry, or it's light outside, or it's dark outside, and all those things can influence detection probability, so we want to control for those. Behavior. Animals that have been captured before maybe have different behavioral responses to subsequent recapture than animals that have never been caught again. Habitat types, sex types, length, weight, sex, all of those things could be used as observable sources of variation and therefore lend themselves to use as individual covariates, environmental or otherwise. If you have unmodeled heterogeneity, you might say, well, what are you going to do? It seems like it should be impossible, right? How could you model heterogeneity when you can't actually see the sources of the heterogeneity? And the answer is, well, you can't perfectly, but there have been a couple of things that people have tried that can actually work pretty well. And we're going to look at two of them. One is based upon what's known as a finite mixture model, or just mixture models in general. They can be continuous mixtures or finite mixtures. And in Mark, we primarily dichotomize between a finite mixture model and something called individual random effects, which is, to some degree, could be argued as a continuous mixture model. All right, so a couple of pictures will make it clear what the distinction is between these two things. So here are the two sort of standard approaches for unobserved heterogeneity. These are available in Mark. These are what you'll find in most of the literature. And so let's talk about them a little bit. So the discrete mixture model pretends that all of the animals in a population could be defined or assigned to discrete mixtures. So in the numerical example we ran through a few minutes ago, we actually did this. We said, well, some percentage of the population are high encounter individuals, some of them are low, but in the process of making that statement, we were dichotomizing individuals. We were saying you're either a high capture individual or a low capture individual. So we, in that case, had two different groups of individuals. Well, that's kind of what you see here on the screen, or excuse me, on the graph to the left. We have two kinds of individuals. In this case, we're talking about survival, but the principle is the same. Some have low survival probabilities, some have high survival probabilities. Substitute in the word detection probability, and you have the same thing. So the discrete mixture model says, okay, you're in one or the other. Now, it's contrasted on the right here with essentially a continuous mixture model. So in the continuous mixture model, you imagine that individuals are sampled at random from some distribution. There's a mean and a variance. And so there are distributions that you might use that you think would reasonably capture the true underlying distribution of latent probabilities of encounter, which you can never know. Right? So you're guessing. You could say, well, maybe it's, in this case, continuous logit normal. Now, what's the main distinction between these two things, other than they look different? Well, the continuous logit normal requires imposing a distribution on all your data. The discrete mixture model basically is going to use a clustering algorithm. It uses something which is going to assign an individual probabilistically to one or the other. So the advantage of the discrete mixture model is it's easy, it's quick, and it makes your job, in some senses, simpler, but it rests upon the assumption that it's a reasonable approximation to some underlying distribution. Nobody really believes that heterogeneity or any parameter is distributed in terms of discrete mixtures. Nobody believes that that's true, but this is an approximation, and it's an approximation that works pretty well. This is much more likely to match reality. Now, we don't really know for sure what the appropriate distribution is, so the default parsimonious one is to assume it's normal. We assume it's normal on the logit scale, which is where we're doing the analysis, so this is a continuous logit normal approximation. The downside of doing this is computationally it takes a whole lot more work, and you'll get a glimpse at that a little bit with some of what comes in the next few slides, and how we do that on a computer. We'll look at a Mark example. The pendulum has swung pretty dramatically towards using these continuous logit normals, but they do require a little bit of a faster computer and a little bit more sort of understanding of some theory. But implementing them and doing them in Mark is straightforward. So we'll actually have a look at them. We'll start with mixture models. They've been around longer. They get used in lots of different disciplines. The fish squeezers, the fish biologists use mixture models with some frequency based upon length at capture data. These get used a lot in chemistry. They get used a lot in physics. So discrete mixture models have been around for a while, and they're, as I mentioned a moment ago, they're really easy to implement. So, why not? And it turns out, based on lots and lots of simulations, they do remarkably well for a lot of problems. It's just that we don't think that they're the perfect solution, and we're now slightly more engaged with the continuous logit normal mixture that I mentioned a moment ago. But let's look at discrete mixtures for a beginning. So we imagine a discrete set of groups. Usually it's 2, sometimes 3, anything more than that, you start running out of data. And obviously, eventually, if you had one mixture group for each individual, then you're back at that situation that we said is not possible. So it's an approximation. So discrete groups, each with their own detection coin. So we consider the population of animals as being a combination of 2 or more mixtures, each with a separate but unknown detection probability. And what we do is we estimate a mixture parameter, which is usually pi. That's the probability that an animal belongs to mixture A. It doesn't have to be A, but let's just say that we have 2 mixtures, A and B. So if pi is the probability that the animal belongs to A, then 1 minus pi is the probability that it belongs to the other mixture. So this is what you would see if you had what's called a 2-point mixture group. So 2 points simply meaning 2 mixture groups. So pi for one group and then 1 minus pi for the other group. You're either in one or the other. So more formally, this is what you're actually seeing here. So you imagine that the p for each individual is either A or B being the 2 groups with probability pi or 1 minus pi. What does that do in terms of your encounter histories? Well, perhaps not surprisingly, it simply adds a little bit of bookkeeping. All right, so let's assume we've got 4 occasions with detection varying by time, and we have mixtures, 2 mixtures, A and B. So here's our encounter history, 1, 0, 0, 1. So what the probability expression is for 1, 0, 0, 1 would be, okay, there's some probability pi that you're an A mixture. And then if you're A, then there's PA1, 1 minus PA2, 1 minus PA3, and PA4. So if you simply look at the probability part of the expression, the encounter probability, that's normal. The only thing that we have that's new is that in front of it is this probability pi that is actually in that mixture group. Or, and remember, or is plus in probabilities, or it's in the other group, it's in B, so that's 1 minus pi A, and then there are the probability expressions corresponding to B. So we basically have added a new parameter, it's pi. What's the probability that you're A or B? And so based upon the frequencies of encounter histories, what the algorithm and the likelihood maximization of that, or the algorithm that maximizes the likelihood will do, is it'll figure out what pi is. And if it knows what pi is, then it will say with some probability with the individuals up here or down here. Now, for the continuous logit normal, just to make sure everybody understands, we imagine that each individual is sampled from some underlying distribution, and that distribution is characterized by a mean mu and a variance sigma squared. Okay, so in the mixture model, every individual either goes into one or the other. In the continuous normal, logit normal, you're assuming that it's sampled from a distribution, so that what are the parameters that you estimate? The parameters you estimate are mu and sigma squared. You don't assign individuals to anything, you simply estimate properties, or formally what are known as moments of the distribution. All right, so hopefully it's not too early or too late in the day for you to look at something like this, but this is basically what happens. So let's start with the stuff that's familiar. What we're saying is that the logit of the encounter probability for an individual is given by something, and that something is the linear model beta plus epsilon. So where is this? So what we're imagining is that each individual has its own little probability, its latent probability, and it's sampled from a distribution. So what this gobbledygook down here is doing is it's doing something called integrating out the individual differences. It's integrating out this function. It's calculating the integral, essentially, of this distribution. Now, we're not going to talk any more about it than that. It's based upon something called Gauss-Hermite quadrature. There's a paper that Gary mentions in his talk about a paper that he and I wrote where we go into this in some detail. It's also talked about in the book a little bit. We're not going to worry about it. You can either do it with Gauss-Hermite quadrature, and the advantage of that is it's likelihood based, so we can use AIC, or you use Markov-Chain Monte Carlo in a Bayesian context, which is what a lot of people do. Either way, you're integrating out the random effect, and when you do that, you can get everything that you want. All right, enough of that kind of silliness. And again, this is explained in the book, so I think I'm going to skip this here. All right, let's actually see how you do these things. And they're not that difficult to do. They're bookkeeping, but I just want to show you various things here. Okay, so let's start by hopping out of PowerPoint for a second. Oops. And we're going to make use of a file called mixed_closed1.input. So this is one where there's a mixture. There's truly a mixture. Somewhere in the book, there's a reference as to what the actual mixture proportions are. I'm not going to worry about that now. I'm just going to analyze the data. So I'm going to go ahead and start program mark, and I'm going to start a new project. It's closed captures, and I'm going to use Huggins heterogeneity pi p and c. So heterogeneity pi means mixture. The pi parameter shows up for the mixture models. So in mark, when you see heterogeneity pi, that means the mixture model, P and C parameterization. And remember, the Huggins model does not have abundance in the likelihood. It doesn't have F0 in the likelihood. And we'll see that in a second. So in part A for this, I mostly use the full likelihood stuff here. I'm going to use the Huggins just so you see both. And the Huggins is actually an easier one to use. Okay, so this is going to be a demo of a two-point mixture approach. I'm going to select my file, which is called mixed_closed1.input. It's got 9 occasions, but you don't know that, I do, but let's look at it. Nothing changes. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's my encounter data. Make that 9. And now you'll notice at the bottom, it's because we picked the mixture heterogeneity model, this little mixture button is available. So it defaults to 2, and that makes sense. You need at least 2 mixtures to have a mixture. You need at least 2 groups. You can make it 3, 4, 5, whatever, but I can tell you from lots of experience that 2 is typical, 3 occasional, 4 I've never seen except fooling around with things. So 2 as a default is fine. Click OK, and away we go. And now we see something that's a little different. What do we see here? We have a PIM with 1 cell in it. Well, that's because what you actually see here is the pi parameter. In the PIM chart, the pi parameter comes first. And then we have P and C. So remember abundance estimation, 2 parameters, P and C parameter. But you may wonder to yourself, if there's only 9 occasions, then why is it that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 parameters for the P group? Well, there are 9 occasions, and I have 18 parameters, and 18 divided by 9 is 2. And that's your clue as to what's going on. If we open up the P PIM, you'll see what the situation is. There it is. You have 9 parameters. It's just that you have 9 parameters for 2 different groups, 2 different pi groups, the high encounter probability and the low encounter probability. So 2 through 10 for one group and 11 through 19 for the other group. Okay, so nothing's changed, but now you have twice as many parameters to play with because you have 2 groups. Same thing applies if we go into our PIM chart and we look at the C parameter. If we open that up, we'll see basically the same thing. 2 rows, each corresponding to the different pi group. Okay, now we're going to work through a bit of a laborious thing here, but for the moment, I'm just going to run this model and I'm going to call it starter. And I do this with some frequency for these models for reasons that I think will be obvious in a moment or two. And this is the one that I built with the PIM. Now, for a lot of the reasons we talked about last lecture, this is not a particularly good model. I don't have any constraints on P and C. So I'm going to have weirdness. I'm not going to use this as a model for inference, but I'm going to use this to build my general design matrix. So I'm going to click OK to run and add the results to the browser, and there it is. Okay, so if I were to look at my results, I get all sorts of signs that I have problems. So this is standard errors that are too big, confidence limits that go from 0 to 1. So this is a garbage model. There's my estimate of pi, which is a garbage estimate. And so there's nothing particularly useful about here at all, except now I have something against which I can test my ability to build a design matrix. So the design matrix for mixture models is not difficult, it's just cumbersome and time consuming, but I want to run through it. It'll help reinforce linear models, and then I'll show you the shortcut trick so that you don't actually have to build them by hand. Okay, so here it is, and it's pretty ugly looking until you step through it. So in my shorthand notation here, what we have is an encounter group, right? So this is the same thing that we did in the last lecture, where we have a separate group for the P parameter and a separate group for the C parameter, much like we had separate groups for young individuals and old individuals for age models. So there it is again. So if you went through the preceding lecture, you saw this. So I think I just called it ENC there, and I'm calling it ENC group for some reason here. That's fine. But now I've also got a heterogeneity group. I've got these two heterogeneity groups that are defined by this parameter pi. With probability pi, you're in one heterogeneity group. With probability 1 minus pi, you're in the other heterogeneity group. And then you've got time. Okay, so those are my main effects: encounter group, heterogeneity group, and time. And then, as is usually the case, you have all the stinking interactions, which is where the challenge and the drudgery comes. So I'm going to have encounter group by time, heterogeneity group by time, and then encounter by heterogeneity by time, and so on and so forth. And in fact, there's one missing here. I also need encounter group by heterogeneity group in there as well. So there's actually a little mistake, and it's down here. I just didn't enter it up here, and that's something I should go ahead and fix, but I'll do it later. Okay, so here it is in sort of conceptually. Here it is in terms of the betas, so my intercept, encounter group, heterogeneity group. And then I've got my time groups, my encounter group, heterogeneity group, so on and so forth. And it's pretty clunky. I got 34 terms in this thing to work through. Okay, it's a pain, and it's big, and it's ugly. And here's what it looks like. And I'll see if I can zoom in a bit so you can get at it. And then, maybe we can just use this, and I'll defer actually building it, because you don't want to build this. All right, so if you can see that, hopefully you can. In fact, let me see if I can make it even bigger. Just the one in virtue of doing things this way. There we go. Okay, so there, way up all by its lonesome in the upper left-hand corner is the pi parameter. There's the intercept parameter, there being what I'm waving over right now. Let me, yeah, I guess I can leave that right. Here's my encounter group. Okay, so this is for my P parameter. And if you look, there's the P parameters, rows 2 through 19, and there is the coding for that. And there's the C parameters right below it. And remember that if I have 9 P parameters for an encounter group, I have 8 C parameters for that encounter group. So there we are, encounter group, and there's my heterogeneities. There's, let's say, the type A individuals for the P parameter, and the type B individuals for the P parameter. Type A individuals for the C parameter, type A individuals for the C parameter, type B individuals for the C parameter. And you can already see it's getting to be a pain. And there's the time codings. And remember, the C parameter starts in the second interval, so it's offset by 1 a little bit. Here's the interaction of the encounter group and the heterogeneity group, and so on and so forth. So there's all the interactions, and I guarantee you can do this. Now, here it looks like I'm actually using the full likelihood model, but you get the basic idea. It's not hard, it's just clunky, and it's easy to make a mistake because it's easy to get in the wrong row or just miscount something. Okay, so we don't really want to, excuse me, ugh. All right, so clearly this sort of design matrix of this size is not something that you'd want to build routinely by hand. It's doable, it's just not particularly pleasant. So the good news is that there are several built-in features in Mark, and particularly in the form of predefined models, which is going to make this a whole lot simpler for you. And so here are the predefined models that we're going to look at in a second with a particular data set, or the data set we're working with, rather. And their standard notation and our expanded notation, but basically M0, MT, and MB, and all those sorts of things. Anything you see the first 4 models are all sort of standard models. We call them Otis models. And then down here with H2 for heterogeneity with 2 different mixture groups, these are the mixture models. So if we ran all 8 of these, then we actually have some models with heterogeneity and without. We could see how well they do. And these are predefined in Mark, and that's very useful for us because that means that we don't have to do any of the laborious work of building all those design matrices. Now, I've said before with the predefined models in Mark, you don't routinely want to use those because it's cheating. and you're not really thinking your way through, and you're simply getting Mark to do a lot of stuff for you. And for everything that we've done up until abundance estimation, that's a fair concern to have and a fair warning and suggestion that you don't do that. Abundance estimation is a little bit different. Abundance estimation, you got one goal, and that's to come up with your most best defensible estimate of abundance you can, which means model averaging, which means you're going to build a lot of different models just to explore the model space, and you're not quite as concerned about sort of a priori biologically motivating the models with anything that you think is biologically relevant. So data dredging, or just sort of trying some version of all possible models or lots of different models, just to get to the point where you can model average, is okay by and large for abundance estimation. So let's actually see how you do that. Okay, I'm going to hop out of PowerPoint here. We'll go into Mark, and the data set that we've been working with, that mixed closed data set, is still there. So I'm going to run predefined models. We select our models, and there they are, 1, 2, 3, 4, 5, 6, 7, 8. So the H2 is two-point mixture model for heterogeneity. These random effects models we'll get to in a second. We click OK to run. There we go. We run them, and they run very quickly. There's our models, and no muss, no fuss. So this is quite a good starting place with respect to building these models. If you right-click on some of the heterogeneity models, you'll see that you're given the design matrix. That's convenient if you now want to modify them further by adding individual covariates or some bits of observable heterogeneity that you might have. You can do that here, and you don't have to build everything from scratch. All right, so now that we've got a bunch of models in our browser, and we can see by looking at the AIC weights that we have a little bit of model selection uncertainty, what do we do next? Well, we model average. This is always what you're after with abundance estimation. So we model average, we output, model averaging. It's a derived parameter. There's only one checkbox to check because abundance is what you're estimating. So one parameter, abundance. Click it, click OK, and there's our estimate of abundance. 1,993.2426. That's the weighted average abundance estimate. That's what you would report. There's the unconditional standard error. That's what you report. And here's the confidence interval, and that is what you do not report because it's wrong. It's wrong because the usual way that you calculate a confidence limit is the parameter value plus or minus 1.96 times the standard error. And that's okay if the parameter that you're looking at is negative to positive infinity. So if it's something that can go to negative infinity or up to positive infinity, you're fine. But abundance is not one of those things. Abundance can't go any lower than 0. You can't have negative abundance. So you can't use that as your estimate of the confidence limit. So the default in Mark is to simply do 1.96 times the standard error being the unconditional standard error in this case, and that's where these numbers come from, but they're wrong. And so what you need to do, this is the one little annoying thing, but it's not the most difficult thing to do, so I'm not going to feel too bad for you or anybody else, is you need to do it by hand. You need to do this little part of the exercise by hand. So here's how you do it. Okay, and this is all laid out in detail in chapter 14, so I'll just show you the highlights here. So just as we did, model averaging, the derived parameter, there it is, you click derived, and you're okay, except that the 95% CI is wrong, so you need to do it by hand. And to do that, you have to do this. And it looks scarier than it really is, but it's not bad. M at t plus 1 is something that you know. That's the minimum number known alive. It's the number of individuals seen at least once. So you have that. That's in the full output, so you simply write that down. There's part of what you need for this equation. Okay, you need to have F0. Well, you know what the estimate of F0 is because it's the abundance estimate minus M at t plus 1. Okay, so you got your model averaged abundance estimate. You know what M at t plus 1 is, and so you simply have to do that calculation. Okay, now C, it's not the count, it's this gobbledygook over here, but it's not too bad. You need the variance for your model averaged estimate, and the variance is just related to the standard error, and you can transform from the standard error to the variance. You need F0, which you get over here, and then you're taking the square root of it on the log. So I'm not going to go into where this equation comes from, but that's all you need to do. You need m at t plus 1, you need your estimate of f0, you need your model average estimate of n, throw everything in these things and stick them back up here, and that's how you estimate your standard error. Now, or excuse me, your confidence limit. And the confidence limit's important. It tends to be sort of especially important for abundance estimation, because often you're going to use abundance to answer questions like, is the population bigger or lesser than some threshold, where that threshold may be important for a conservation management decision. And so you report the estimate, and then you say, here's the confidence limits, and you'd like the confidence limits to be correct. And so in order to make them correct, you have to do this. Now, there's a worked example in chapter 14. So this is just sort of a preview of what that's going to look like. So once you get to that point, you'll know kind of what's coming and what to do. It's not difficult. It's just kind of a nuisance. It might take you 5 minutes at most to do this, but you only need to do it once, and you need to do it for your model average estimate of abundance. Okay, so that's model averaging, and regardless of how you handle heterogeneity, that's what you need to do. I want to just show you the random effects stuff and how you do that in MARC. So I'm going to take the exact same data set, but I'm going to use the random effects approach. So this is, again, this idea of a continuous logit normal distribution of individuals. And I'm going to select the file. I'm going to use the same file, so MARC will warn me that I'm going to overwrite the results. It's closed captures, and there's my Huggins PNC with random effects. Click OK, click OK. There's the warning that it's going to overwrite the previous results. That's fine. Previous result, the model average was about 1,993. And now we're going to simply redo the analysis, but just use a random effects approach. Click OK, click OK. And I'm going to go ahead and jump right into the predefined models. The predefined models, again, are here. We select them. I'm going to do the 4 standard models without any heterogeneity. And now I'm going to use these random effects models. So the RE is for random effects. I have 8 models selected. I run them, but they take much longer to run. And this is the reality that we need to deal with. When you are running random effects models, they are much, much slower than running models that are just without any heterogeneity or mixture models. But eventually they'll finish. Sometimes they'll take a while, but they'll finish. And then we're left with our models in our browser. So let's just finish this one up. I think I have one more after this, or is this the last one? No, that's the last one. Okay, so I do model averaging. So model averaging again, derived, there it is, click OK. And here, my model average estimate is 2,027. So when we did mixture models, it was 1,993, and with the random effects approach, it's slightly higher. Now, for these data, these are simulated data, the true abundance of the simulated data was 2,000. So the random effects model here gave us one that was biased slightly high, and the mixture model gave us one that was biased low. And this is just a reality that depending upon how many occasions you have and what the variance is in your heterogeneity, you can end up with either positive or negative bias depending upon the data, but also depending upon which type of heterogeneity model you fit to the data. And that whole exercise that I just mentioned in so many words was the basis of a paper that Gary White and I wrote a couple of years ago, which he mentions in his talk, and all the details are there. So there is no perfect solution to handling heterogeneity. There are just some solutions that tend to do better depending upon the nature of the heterogeneity, which you don't know, but also depending upon the number of encounters histories that you, or not the number of encounter histories, but the number of occasions that you have, and the sort of overall mean encounter probability. Worst case scenario is a situation where you have very few occasions and a low encounter probability. In that case, don't actually bother to try, because whatever estimate you get is going to be wildly biased. But if you have 5 or 6 or 7 more occasions and some level of heterogeneity, then the mixture models or the random effects models tend to work quite well. And in our experience, our being Gary and I, the random effects models tend to have really, really nice properties. They work pretty well and in our minds, at least, they seem more realistic to begin with. Okay, so that's really all I wanted to talk about in the second part of the abundance lecture. All of this material, as I mentioned, is in chapter 14 in the book. It's a chapter that was originally drafted, very short draft, by Paul Lucas. I think the original version of the chapter was like 12, 13 pages. It's now 70 or so, so I've added a lot of stuff to the material. I don't think Paul would recognize his chapter, but since he did the initial draft, I keep his name on it. It doesn't really matter who gets credit for these things anymore. So when we get to the point where we're going to do some abundance estimation assignments, I will send you the sections of chapter 14 that you're going to be responsible for. Okay, everybody. Well, I hope that was successful, and I will talk to you next when we start looking at open population models. We're going to do sort of the extended version of the Cormack-Jolly-Sieber. We're going to look at classic Jolly-Sieber and some other really cool models that I think are going to be particularly important for us to move forward. At any rate, hope everybody's staying healthy. Have a good day, and I will talk to you soon.